Hi, my name is Nagar Romy, and this is Lab 5, where we look at Faraday's Law. The purpose of this lab is to understand Faraday's Law while understanding flux, and to compare experimental observations with a computational model. Our results were that the experimental time was 1.813 seconds, and the computational time was 1.725 seconds. The fundamental physics principles at hand were Faraday's Law, Lenz's Law, and Newton's second law. In the experiment, our system was the magnet and our surroundings was the aluminum tube. We made the assumptions that air drag is negligible, that we had an ideal powerful magnet, and that the bar magnet acted as a magnetic dipole. Our initial conditions are the following on the screen. The process was to drop a powerful magnet straight through a conductive non-ferrous tube and see it fall out the other end. In our case, we used a tube of aluminum. We predicted the magnet would fall down as normal, but we observed that the magnet fell slower than normal, so there must be external forces present that slow the acceleration of gravity. And again, the average fall time after 5 iterations was 1.813 seconds. Here's the code that we ran where we had our initial conditions set up, where we had a function that imitated the magnetic dipole, and then a function where we calculate the flux caused by the magnet going through the aluminum tube, and where we have Newton's second law, so we see the movement of the bar magnet through the tube. And the image on the right shows the magnet falling through the tube with the north side up. And here is the graph we achieved. And in the beginning, we see that the force of gravity is greater than the magnetic force. And then about 0.3 seconds in, it levels out. So we see that the force of gravity is equal to the magnetic force since the velocity is staying the same. So there's no one force greater than the other at that point. And then near the end, the force of gravity is greater than the magnetic force again. The intensity of the color of the tube indicates the magnetic current flowing through each ring. Red and blue indicate current following in opposite directions. Which color corresponds to the clockwise current and which one counterclockwise? How do you know? Red is counterclockwise and blue is clockwise, and we know this due to Lenz's law. Now, what happens to the dynamics of the system when you flip the magnet around? The magnitude velocity would stay the same, the current would just be flipped. How does the total time in tube of your real-world system compare to that of your computational system? How might the computational system be made more accurate? They were similar, but real-world was a bit longer, probably due to air drag and imperfect objects being used. Adding more rings to the computational model would help. And what does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? When entering and exiting the tube, the force of gravity was greater, but when it was well inside of it, it was equal to the force of the magnet. So it tells us that there's probably something to do with air when you first come in and come out, but in the middle, they are about the same, hence why it moves so slowly. Now, what if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? We know that with Ohm's law, V equals IR, so a decrease in resistivity would mean an increase in current. Therefore, the magnet would fall slower. Now, if there were holes or slots in the tube, how would this affect the ring's current in your model? Since there's less surface area for the magnet to pass through, there's less flux, so the magnetic force is less to counter gravity. So the magnet would fall faster. And we conclude that possibilities of error are not accounting for air drag and human error and timing. But overall, we saw that with an induced current, we have a magnetic force present that can counter any other forces like gravity and show us that magnetic braking can be present, like in this experiment. Thank you.